Alright, so in this particular video, I'll do a few force practice problems. That includes multiple choice and just free response. The first one is this particular vertical problem. So essentially, this particular mass is being swung in a vertical loop. The length of the string is 0.45 meters, and then the mass of the bob is given as 0.5 kilograms. And it says that it's moving at a constant rate of 120 revolutions per minute, and that's essential. We'll have to do a little conversion in just a second, okay? Ultimately, it wants us to find the magnitude of the tension in the string at the lowest point. So here in this diagram, the bob is already at the lowest point. It wants to find tension. So I would just go ahead and draw my free body diagram for a vertical loop or vertical tension problem. So here's f of g. The weight of the bob, which is be directed down the page or down the screen. Tension is going to be pointing up along the string towards the pivot where the string is being tied to, or the hand, whatever is holding it, in order for it to spin in a vertical circle. Okay. I do want to point out that for these types of problem at the lowest point, your tension is going to be greater than f of g because the bob is going to essentially have to move up along this vertical loop. So T would have to be greater than f of g for that phenomenon to occur. All right. So I'm just going to go ahead and set up f of c. F of c is just the sum of these two vectors along this line of motion here. Okay, along the line of the string. Excuse me here. So here we have t pointing up along the string. At the same time, though, f of g is pointing in the same line, opposing the tension in the string. So essentially, because these two vectors are pointing opposite, we'll just end up subtracting. So here I make the statement: f of c is the net force resulting in this particular line along the string. So I would just say T minus f of g. Alright, so on the left side, I can just expand f of c into its definition. That is mass times the speed square divided by r, and that's equal to T minus f of g on the right side. Again, focus on what the question is asking for, is looking for tension. So I like to go ahead and manipulate functions so that I can get my variable by itself. So here on the right side, you notice T minus f of g. To get T by itself, I need to move this negative f of g. So I'm going to go ahead and do that real quick. This is a negative f of g, so I will move it to the left side, which causes it to become positive. But f of g is the same as mass times gravity. So I kind of did two things in one there. I moved it and I substitute out f of g for just mg. Okay. mv squared r stays as is because I haven't touched it yet. So in this case, I'll just go ahead and plug in values. M is given as 0.5. V, I don't know what V is. It says it's 120 revs per minute. So make sure you look at units. Just make sure you look at units and not just look at the number, okay? Because otherwise, if you plug in V as 120 here, you would be goofing and would get this particular problem wrong because it's 120 revs per minute. So pay attention to units. Here, R is given as 0.45 meters because that's the length of the string. As it rotates, the length of the string becomes your radius. And then the mass, once again, M here is 0.5, and then G. Notice here I plug in 9.8 because the negative sign was already taken care of for you from the initial statement with the minus f of g. So be careful where you plug 9.8 versus negative 9.8, okay? I personally like to get my negative signs out of the way, so when I plug g in my work, it's positive 9.8 here. Otherwise, you are going to get a different result. So that's that. So as you can see, the only thing I highlighted here is V, right? I don't know what V is in meters per second. The problem states it's 120 revs per minute. So I will go ahead and show you how to convert revs per minute to meters per second in case you don't know how. So I'm just going to start with basic conversion steps here. I'm going to start with 120 rev for revolutions per minute. I'm going to convert it to meters per rev. Now, you notice here the units at the very start, rev is in the numerator. I need to cancel revolutions out, so I need to put revolutions on the bottom. But one revolution is just the circumference of a circle, right? Anytime you complete one circle, that's just 2 pi r. And 2 pi r is quote unquote the distance of a circle. It's the circumference. Okay, so I just cancel rev out. The next thing I need to do is cancel minutes out. Well, minutes on the bottom here, I need to put it in the next conversion step, and that is minute needs to go on top. For every minute, there are 60 seconds, and that's where there's 60 seconds on the bottom. So as you can see here, the only thing left really on the top is 120 times 2 pi times r. But once again, r is 0.45 meters. So instead of revs, I just convert it to linear distance, which is meters. And on the bottom, minutes cancel out. Ref already canceled out. The only thing left over is 60 seconds. So ultimately, you have 339.292 meters divided by 60 seconds. If you punch on your calculator, you get roughly 5.655 meters per second. Okay, so this is how you would convert revolutions per minute into meters per second. All right. Other than that, now that I have V in meters per second, I can just go ahead and plug in Chuck real quick. Okay. So I'm just going to carry my work down here. Everything stays the same except for V, where I highlighted V in yellow. In parentheses here is just what I just calculated, what I just converted. I wouldn't say calculate, I just converted. It's 5.655 meters per second. And then make sure you square that. And if you do this correctly in your calculator, you should get roughly, the first term is 35.53, and then 0.5 times 9.8 is just half, which is 4.9. And if you add those two values, you get about 40.43 newtons, and the closest answer would be E. Okay. All right, so that is that for this particular problem. The next one is this one. Here it says planet 1 orbits star 1, planet 2 orbits star 2 in circular orbits. So this is key. It says circular orbits of the same radius, right? So both these planets orbit two different stars, except they have the same radius. So that's a key factor here. It says, however, the orbital period of planet 1 is longer than the orbital period of planet 2. Now, what does that mean? It just means that planet 1 takes more time to complete one revolution, right? So it says, what could explain this? So here are your answer choices. If you need to pause, read A, B, C, D, E. On that, I'm just going to show you how to crack this out. You're ultimately asked to explain why planet 1 takes longer, right, to orbit. So I kept track of what the statement that was important. It says here, T1 is more time than T2, right? If you're, I guess, orbital period is just T, in case you're keeping it. T here is not tension, T here is time. In physics or in mathematics, the word period triggers capital T. Again, T here is for the word period, not tension, okay? So period 1 is greater than period 2. And period is the time that it takes to go one revolutions, one cycle, all right? So if we think about this particular problem, it's the planet orbits in a circular motion, so hopefully it triggers, this is a centripetal force problem. So here I just made a statement. I said centripetal force is equal to the force of attraction between the planet and the star, right? So this is a generic statement that I can apply to both stars. Well, on the left side, your centripetal force, because these planets are orbiting in circular motion, it can just be replaced out for m v squared. Now, which v? It would be the mass of the orbiting object. In this case, the star is going to be stationary, and it's the planet that is revolving, right, orbiting around these stars. So the mass on the left side needs to be the mass of the planet, and r on the bottom is from center to orbit, right? On the right side, the force of attraction would just be between the two masses. In this case, it would be just the mass of the star and the mass of the planet. You just have two systems, that's all. So you would apply this particular function twice. So what I'm going to do though is I'm going to go ahead and cancel stuff out that I can, simplify this particular function. So m of the planet appears on both sides, so I can just cross that out. Now, if you look at the answer choices though, right? If you took a second to read it, choice C said planet 1 has less mass. Well, that doesn't matter, because if you have been keeping up, the mass of the planet in this particular generic function cancel out. So I can cross out C. I can also cross out D. The mass of the orbiting planet does not control the orbital period. It's the stationary object, which in this case would be star 1 and star 2. So I'm just going to go ahead and simplify this function down on this. So on the left side of my work, v squared is the only thing left over. On the right side, it would be Newton's gravitational constant and the mass of the star, right, over the orbital distance from center to where the orbit is. So as you can see here, if I were to solve for v, I would just take the square root of both sides. All right. So you notice here I highlighted my work m star. Well, that's because the radius here for both objects are the same, because it said so. G is a universal constant. So the only thing that really matters in my work here is m star. The mass of the stationary star dictates how fast you can orbit, right? So in this case, what I'm thinking is, look, if the mass of the star is small, right, and the mass of the star is in the numerator, when your numerator is small, you're square rooting a smaller number, when you square root a smaller number, well, you get a smaller answer. So when m star is small, v is also small, or slow in this case, right? Well, if v is slow, then it would take more time to orbit the same orbit because it says that they have the same radius. So the orbit would be the same because of the radius being the same. All right. So I made a note for you here. This is how I think about it. If the mass of the star, which is the stationary mass, is less massive, if it's less massive, the numerator is small. Well, if you have a small numerator divided by the same r, you get a smaller answer, right? So therefore I say v is slow. Well, if v is slow, then it would take more time. So in this particular problem, it says the orbital period of planet 1 is longer. Well, it's longer, so therefore that implies that it takes more time. Well, why would you take more time? That's because you're moving slower. So in this case, I would choose choice A, right? Planet 1 takes longer to orbit because the mass of star 1 is less massive. Well, if it's less massive, it pulls less. If it pulls less, your orbital speed is less. All right, so that's how I think about this particular problem. Let's do this particular one. As here we have a conical system. It says a mass of 4.7 kilogram is suspended from a string, and then it revolves in a horizontal circle of radius 86 centimeters. I do want to point out here, as I read these types of problems, I always pay attention to units. This says 86 centimeters, not meters, so make sure you pay attention to units. And it says the tangential speed of the mass is 2.97 meters per second, and it wants us to find the angle between the string and the vertical. So I found a diagram here that dictates that, right? The theta that I found in this diagram touches the vertical. So pay attention to wording, pay attention to where the angle is placed. The angle don't always have to touch the vertical. For this particular problem, it is. Sometimes your angle touches the horizontal. When that time comes, you just have to make sure your geometry is on point. All right, so let's do it. To find the angle, I'm just gonna go ahead and draw my free body diagram like I have been this last couple of problems. So here's f of g for this particular conical system. Here's the bob or the weight or the mass, whatever you want to call it. It's pointing down the page. And here's the tension. The tension is going to be pointing towards the pivot wherever it's being tied to or held to. All right, so it's going to be pointing in the northwest direction. And then from there, I can just go ahead and call that t. But that t is a diagonal, so it has to have components. This is ty, and vice versa. This is tx. Okay. Well, if you look at this particular diagram, or if you've been studying your conical stuff, you just have to identify, well, what is the force that's pointing towards the center of this particular orbit, right? So here I'm just going to break my work up into x and y. So on the x side, if you look at this diagram, the only arrow that's pointing towards the center of this particular horizontal plane for this conical pendulum is tx, right? Tx points left at this point, but if you visualize it, when the bob's over here, tx will point right, but regardless, it also points towards the center of the circle. So that's what's causing your centripetal force, right? Your centripetal force is the force or the force component that is pointing towards the center of the circle. In this particular problem, tx is the only one. So I'm gonna go ahead and say that my centripetal force is contributed by tx. Well, I want to break this up. Well, once again, Fc is simply mass times speed squared. What speed? Your tangential speed divided by the radius of this particular orbit, right, equals to tx. Now I can go ahead and break up tx. It's important that you pay attention to your geometry, right? The angle given here is touching the vertical axis as stated in the problem. So if you look from this angle and you look across, tx is actually your opposite. Opposite would trigger the trigonometry function sine, right? So here I would say tx is t sine because tx in this diagram is the opposite leg. So pay attention to where the angle is being placed. Don't memorize stuff. All right. So in that, I know what m is, I know what v is, I know what r is in centimeters, and the only thing that I really don't know is t, right? Ultimately I'm trying to find theta. So the only thing that I don't know in the statement is t. So I'm going to go ahead and move to my y side, right? These problems kind of force you to substitute out stuff that you don't know. Well, if you look in the y direction, you have two arrows. You have a ty pointing upward, and then you have an f of g pointing downward. The bob is not allowed to oscillate up and down. It's just tracing out a horizontal plane, meaning it's not moving in the vertical direction, right? It's just keeping, it's like a pizza. It just stays flat, right? So here on the right side, I'm going to go ahead and expand this work. F of g, by definition, is just mass times gravity. Ty in this case, so if you look at Ty right here, right? Ty that I drew in my diagram is here. This is actually the same as drawing over here where my cursor is going back and forth, right? That if that's the case, this side here is your adjacent, and if it's your adjacent, cosine needs to be in your forefront. So on the right side in the y column, f of g once again is mg. Ty is t cosine of theta. So I don't know what t is. I know what m is. I know what g is. Ultimately, again, I'm trying to find theta. So I'm actually going to solve for t here so I can substitute it out on the left side. To solve for t, I will divide both sides by cosine of theta. So on the left side here, I just made a statement. It'd be just mass times gravity because that's in the numerator. And I'm just going to divide it by cosine of theta, that it's equal to t. Well, now that I know what t is equal to, I can just substitute it out on the left side in my work. So mv squared over r stays the same, except for t where I highlight in green. I can substitute it for mg divided by cosine theta, which I just found on the right side. As you can see here, the mass of the bob cancels out. Okay, now if you want, you can go ahead, and simplify this sine of theta over cosine into tan theta, because tangent is sine over cosine. So that's where I got that from. So it would just be g on top, which is carried down, and then sine over cosine is substituted out for tangent of theta. On the left side, v squared over r just got carried down, and then to find theta, algebraically, I need to go ahead and divide both sides by g in order to get tan by itself. So that's why I moved the g from the top right to the bottom left, which is right here. Okay. Now, you notice here, theta is not by itself yet. You still have tan theta. So to get theta by itself, you do arctan. So you just divide both sides by tan. It becomes tan to the negative 1 of v squared over r and g. Excuse me. Now, if you are keeping up, earlier when I read it to you, I did point out that the radius is given in centimeters, so make sure you pay attention to units. This needs to be converted to meters, okay? So I highlight this box for you, because if you don't pay attention to units, you might plug in r is 86 centimeters, which is wrong. You need to convert 86 centimeters into meters by dividing by 100, okay? So therefore, the radius is really 0.86. So when you get down to this step, you would plug in v as 2.97 meters per second. R is 0.86, and then G is 9.8, and if you do that correctly, you should get a value of 46.3, and that is what I got for this particular problem, okay? That's it, okay?